Welcome back to Advent of Code 2021, day 23, continued. Welcome in, Umara. I didn't finish day 23 last stream. I did part 1. And I have a feeling part 2 will be quick. It's just little bit of hard coding needed. So, alright, so part 1 was basically a game of moving these letters around one space by one space and try to get them into their proper positions. So the final state looks like that, and it's basically like a shortest path algorithm for rearranging the letters. Not too hard. It's just fiddly because it's not a non-natural shape. You gotta account for these specific buckets and their locations. So a lot of just hard coding stuff, but it's done. Now, part 2, they've basically just added this stretch to it. So, yeah, I could make my code fit both part 1 and part 2, but I just can't be bothered. We'll just go all in on part 2, which means I have to take those lines there. And that there. Okay. And then if we run this now, it probably won't work. Actually, no, let's not run it. Because we now need to hard code a bunch of things. So, what do we do? Right, so home columns, corridors is the same, movement cost is the same. So we just got to go through these lines and see what changes. That stays the same. Stays the same. That stays the same. Alright, so is path clear? This stays the same. Yeah. Ah, no, not quite. Alright, so let's redo this. Take that out. Instead, we say this will actually work for part 1. I'll still just focus on part 2. We want to add all the spaces above ending on and including the corridor column. So for I in range, so starting from start 0 -1, so we're going up. Ending on one, but we put 2 and then we're going backwards, so we end on and include 1. Yeah. So that this loop actually made more sense than what we wrote before. And then that stays the same. Also, all locks. Let's make that a self variable. Because we're recomputing it a billion times. We don't need to do that. And else. And then if we're in a corridor, it's slightly different. So we say left, right. Okay, so that's as normal. And then we go for I in range, starting from 2. So that's this row, ending on destination. Wait. Yeah. For I in range, okay, starting from 2 and ending on destination row. Yeah. We add I dest 1. That stays the same, because the destination will be given. And so that method's fine. Now this one. So if a car in ABCD will lock in self.locks. So we go through each of the letter locations. If it's greater than 1, we go through an up move. Alright, so we do... If it's in its home column, then we only proceed if it's not. If it's in its home column and everything below it is correct, then we continue. So this line is not quite right. We want to say all below equals be I lock 1 for I in range. So starting from the next space down, so it'll be lock 0 plus 1, and ending on 2, 3, 4, ending on 4. So put 5. Then we say if all of the spaces below, so if all E in E all below. So we're saying everything that's below us is also the correct character. In that one situation, we don't do anything. It's home and it's done. Otherwise, this is in a wrong place. I mean, it could be in a right place, but it needs to be moved because there's stuff underneath it that's in the wrong place. So it is necessary to move it. So now, say corridor, basic corridor. If path cost, yeah, this is all fine. Yeah, okay. And then we go to this case. If it's in the corridor, we want to move it down. Okay. Let's find the top. Find the topmost empty space. So in the home column where it has to go, let's find the next empty space available. What does that mean? Sorry. Okay, this line here is fine. If that space is occupied, then self dot all locks. Hello, DJ. I'm just finishing off the problem from before. Seems fine. I just need to write some hard-coded stuff. In fact, it's actually looking better now because I'm generalizing it more to for spaces, which I'm using for loops for instead of hard-coding index 1 and index 2 separately. So it's actually cleaning up the code. So we've got a thing, and we want to go down into its correct home column. So first we check if the topmost space is occupied. If it is, then skip that. We can't take it home. If it isn't, then insertion point equals, let's say that. And we say, so we're saying if there's an empty space here, we're saying we're going to put it there. However, we look below. If there's an empty space below it, then actually we'll put it lower, and so on. So just say for I in range 3 up to and including 5. If I, the same column, not in self.all logs, then we can say we push the insertion point one space down. So this is gravity. We're simulating gravity. Every time there's a space below it, it drops one step further. So point equals I version 1. Oh, technically it's just this. So we move it down. Else we break out of this loop because this can't be pushed down any further. Alright, so at this point we found the next space it will drop. Now we have to check if everything below that space is correct. So we do this thing that we did before, which was create something called all below. All below equals I column 1 I in range. So we're starting from the next space down, which is going to be insertion point I dot 0 and ends on 5. 1, 2, 3. Hang on, I've got these numbers wrong. It should be 2, 5. No. Oh yeah, it's 3, 5. So we're saying we put it in... What? Yeah, that's 2. And then we check from 3. Oh, I was right the first time. It was 3, 6. We start from 3, which is that row. See if I can move down further. And we end on 5, which is that row. So 3, 6. Okay, yeah, that's fine. Then over here it was... And on 5 again. Okay, that's fine. And then we say... If... To make this thing again. If all P in self.locks car or P in all below, we'll say if not all, then we continue. So that means if there's something wrong down there, that means we shouldn't make this move at all. It's an invalid move. So everything else, we don't need that. And now we check if the path is actually clear to move it there. If not, is path clear, blah blah blah. Okay, good. And then we do that. It's dest. In dest, this insertion point. I should have called it dest. It's not too late, let's call it dest. It's fewer characters. Well, I have to rename because that's what I'm doing. Oh, I meant dest. Rename it to rename. Dest, it was that. Dest, yeah. That means it's not. The lines are not as bulky. Let me do that again. Yeah, bad practice. Copying all this segment again. Should be another method. And then okay, the goal is gonna look like 2, 3, 3, 3, 4, 3, 5, 3. Oh, that's gonna be 2, 5, 3, 5, 4, 5, 5, 5. There we go. Okay, hopefully this works. The code looks more secure this way because we're using for loops. It's going to take longer because it's a bigger problem now. In fact, just adding those two lines could make it take way longer. So I said before that I think A star will actually speed this up quite a lot because especially considering that D is very expensive to move. So we should... None? None? What do you mean none? We couldn't find a solution. Okay. Let me make sure I've Right. Let's generalize this then to part 1 again so that we can test it on part 1. So the depth should be the number of lines minus... Okay, so it's going to be like... Depth equals... Right, so as soon as we finish this, I will be... It'll be I minus 2. 0, 1, 2, 3, 4, 5, 6. We want depth to mean number of, yeah, I minus 2. Depth equals I minus 2. Just make sure that's right. 4, okay. And then wherever we've hard-coded stuff, we need to change it. So we say... That's fine. Where do we use depth? We use it down here. So that should be depth plus 2. That should be depth plus 2. Should be everything we change. Ah. This should be... So it should be 2... No, what? Yeah. 2 plus K 3 for K in range. Yeah. So that'd be 2 plus 0, 2 plus 1, 2 plus 2, 2 plus 3. Yeah. 5. 2 plus K 5. So it'll be like that. Huh? No, 3. I'm gonna change it to 5. And then this one will be 5. And this one will be 7. Oop. These are generators. How did we... Okay. This would be 9. Okay. Still gonna say none, probably. We haven't actually changed anything. And then, is there anything else wrong here? Ah! No, that's fine. Hello, Ezzy PPP. Right, okay. Now, let's delete those 2 lines. Back to part 1. See if it still works. Oh god, I've broken it. Oh, this is gonna be a pain to... debug. How's it going? Going okay. Now I've hit a bug. That's not good. I had a working solution for this and now it's probably an index that's wrong somewhere. Should that be depth plus 1? Wait, I used depth plus 2 down here. Why did I use depth 1? What is the final thing we use? All below equals I in range. So if the depth was 4, final row will be 1, 2, 3, 4, 5. That should be depth plus 2. Like that. Could it literally just be I changed that 1 to a 2? That was the bug. That would make sense. because that variable is very important. Alright, hopefully that works. Be right back. It's going to take longer now because we managed to find more paths. Should have run it on part 1 first. That would... Oh God, still doesn't work. Well, let's try part 1. Alright. We can fix it for part 1, then we're back to where we were, which is good. Okay, we've broken part 1. Wonderful. Hello, SMAP UK. Luckily, you are an experienced developer that uses source control and tests as they refactor, so easy to fix. Yeah. Well, the thing is, I made it more general. I removed all those hard-coded indices and replaced them with for loops, which is technically safer. There's a couple of indices here and there, though. There's a 3 there. What does that mean? Time range 1, 2, 3. Why are we starting from 3? Oh yeah, no, that's fine. Oh. Ah. Should be a +1 there. Did I make that mistake earlier as well? There's a +1 there, so I didn't copy the +1 properly. Try that. We're doing that one. That was definitely an error. That was definitely a bad error, because that would mean we always include that space itself, so that would always return false. 15383 was part 1. 15385. How am I 2 off? I might have fiddled with this. Let me check I've got the correct puzzle input. How can I be 2 off? The right input. How did I define? So that's the goal. And the 2 is like 2 A movements and nothing else. Like how did that happen? Corridors are the same. 0, 1, 2, 3, 5. Yeah, okay. Because I was 2. 0, 1, 2, 3, 4. What on earth could lead to being short by 2? That means we've found a solution and haven't added 2 of the A movements? What? So maybe... So like if the first step was to move A there, that would cost 2. Could it be that we're somehow ignoring first step? Or could it be that we've missed out two over, not 2 under? Correct answer is 15385. So I'm 2 under. So we found a solution that's faster than the actual best. So I've basically somehow not added an edge, like the first edge probably, or something, or maybe the last one. Ooh. Maybe the last one might be more plausible. But that's in Dijkstra. So I didn't modify this, so when do we return early here before we added something somewhere? Just go. Or maybe it's because of this lazy deletion system, but that would result in the worst score. That's weird. So I didn't touch Dijkstra, so what could I have changed in the get neighbors or is path clear? Like, that's logic, so it shouldn't result in... Like, breaking these should just cause us not to find a solution, really. Get neighbors. Like, if you can't find a neighbor, then they shouldn't be able to solve it. Unless... So if we've got a faster score, it's like maybe we accidentally moved through something which saved us energy. Like, it could be... Could be like somehow we moved the C out and then we moved the... I don't know. Yeah, it's probably a result of cheating. Like, say the correct answer should have been to move A here, but we've moved it. That would be more than 2. It's gonna be something like we should have moved A first, but we actually moved C first and then A after, or something like that. I don't know. See. So that could mean the path clear method is still broken. Still got a whole bunch of hard-coded indices here, but up, then left, right. This is just a Boolean. Well, yeah, okay, so are we even using these? Okay. So we define this up here. Alright, let's take a look at this path. So, we're in a bucket, and we want to get from start to dest. So we first go up. So we go from I, starting at space directly above it, ending at what we want to end on 1. So we go wait, this doesn't look right. And we start on that. Okay, example. Start 0, so we start on row here. So that's 1, 2, 3. So we start at 3. So this range starts the next available space up, which is 3 minus 1, 2, and ends... We want to end on 1. Why did I put 2 here? So it would have to be 0 here. Well, that's a huge change. Try that. There we go. We got the right answer. Why does... Oh yeah, because there's oh yeah, because these The spaces above it are clear anyway. Why did that change it then? So... Oh yeah, because we stopped at 2. Okay. So basically, this row here we were ignoring. So we were allowing things to move through the things above. And for the most part, that worked. And that's actually quite plausible. Like, moving B, then A is the same as moving A, then B, if they're using the same distances each time. But there are cases where that's not correct, because things get clogged up and you actually can't do the same thing by letting them go through each other. So, and for the bigger case, that probably becomes a bigger problem. Okay. Yeah, I mean, you can use the case where they go through each other as a sort of lower bound as well. If you wanted to write an approximation algorithm, then you could just let them go through each other, have a lower bound, get an upper bound by finding solutions, but not necessarily the fastest one. Alright, anyway, so then... the big case. So it should take the same length of time. Well, actually, it was quicker because we cut down the branching factor. Like, there were a lot of falses here. 49803. And we managed to generalize it so that it actually works with both inputs. Nice. Okay, yeah, I've figured it would work. It was general enough that that could work for any depth now. Pretty sure I could have just solved the puzzle by hand. The key really is to prioritize D. Make sure D does perfect movement. Probably C as well. Okay. We're on to Christmas Eve. Alright, 1 second. Alright. Christmas Eve. Day 24, Arithmetic Logic Unit. Magic Smoke. Because the like of Dijkstra and A-star are still foreign to me, the simulation was easy, but the solution was hard and solving it by hand. Yeah. I was gonna try A-star, but I can't be bothered now. I think it would be a lot faster than Dijkstra for that, because there is an imbalance with D. Like, it heavily wants to prioritize minimal movement of D, whereas our algorithm is not really caring. But A-star would care a lot about D and C. Magic Smoke. Something. Electrical engineering smoke, okay. I've never heard the term magic smoke. I've done a bit of electronics at school, but not professional electronics, so. Post hoc ergo propter hoc. feel like I should know this phrase. Post hoc ergo. So after, therefore. Yeah, I mean, in mathematics, we've used phrases similar to this, but I've not seen that phrase exactly. After this, therefore, because of this. Since event Y followed event X, event Y must have been caused by event X. So it's sort of like a causation versus correlation type of fallacy. But a bit simpler. It's not quite correlation. It's that happened, then that happened. Brazilian footballer Pele blamed a dip in his. Alright. Vaccine adverse events. Yeah, that's a pretty big case for post hoc ergo propter hoc. Alright. Starts leaking from the submarines. ALU. Without the ability to perform basic arithmetic and logic functions, the submarine can't produce cool patterns with its Christmas lights. It also can't navigate or run the oxygen system. Don't worry though, you probably have enough oxygen left to give you enough time to build a new ALU. The ALU is a 4-dimensional processing unit. It has integer variables w, x, y, and z. These variables all start with the value 0. The ALU also supports 6 instructions. We got imp a, reads an input value and writes it to variable a. Add a b, add a to b, store in variable a. Multiply AB, multiply A by B, and store the result in variable A. Div AB, divide the value of A by the value of B, integer division. Truncate means to round the value towards 0. What does Python do by default? I mean, are we even working with negative numbers? Yeah, probably. I never even thought about that. Towards 0. Yeah, that actually aligns with what I would expect. Okay. Mod AB, yeah, okay. Equal AB. If A and B are equal, then store the value 1 in A. Okay, easy enough. We don't have a whole bunch of others where we do pass by reference, pass by value, etc. In all of these instructions, A and B are placeholders. A will always be the variable where there's... Okay, fine. Or B can be either a variable or a number. Oh. Okay, so we do need to have some sort of inline method, which... Yeah, okay, that's easy enough. The ALU has no jump instructions. Okay, makes it simpler. Once you have built a replacement ALU, you can install it in the submarine, which will immediately resume what it was doing when the ALU failed, validating the submarine's model number. To do this, the ALU will run the Model Number Automatic Detector program, MONAD, your puzzle input. Alright. There's no jumps. Model numbers are always 14-digit numbers, consisting only of digits 1 through 9. Digit 0 cannot appear in a model number. When MONAD checks a hypothetical 14-digit model number, it uses 14 separate IMP instructions, each expecting a single digit of the model number in order of most to least significant. So you would give 1, 3, okay, fine. When operating MONAD, each input instruction only ever be given an integer value of at least 1 and at most 3, 9. Okay, fine. Then after MONAD has finished running all of its instructions, it will indicate that the model number was valid by leaving a 0 in variable z. However, if the model number was invalid, it will leave some other non-zero value in z. Interesting. Okay. MONAD imposes additional mysterious restrictions on model numbers, and legend says the last copy of the MONAD documentation was eaten by a tanuki. This is the Japanese raccoon dog. You can, there's actually in the game, video game, what's it called? Shadow Tactics? Blades of the Shogun. You can, one of the characters you can play as a tanuki. You can like send your tanuki to distract guards and then like assassinate them. I never saw one when I went to Japan. I don't know if people actually walk around with them. I don't think it's the kind of animal you actually walk around with. It's not really a dog, is it? It's a raccoon. They probably have them at events or something. What's it of the order Carnivora? Which is... wait, Canidae, which is... quite close to dogs. Alright. Oh yeah, of course, the Tanuki suit. There we go. You'll need to figure out what MONAD does some other way. To enable as many submarine features as possible, find the largest value 14-digit model number that contains no digits. What is the largest model number accepted by MONAD? How many possible numbers are there? It's 1s and 9s, so it's like 2 to the 14. That's what, like 8,000? number of instructions is that, and there's no loops, so it should just be pretty straightforward to just try them all. You can start from 9999 and work your way down, but I think I even need to. All right. Alright, so... Okay, so the first instruction is imp. Oh, no. And that has, several imps in there. Okay, fine. So we can just say instructions. Okay, so let's just do a split. I guess just put the tuple in, but let's say we put a none. Let's just make it 3 variables, just easier to unpack. So if so tokens tokens 0 tokens 1 we don't actually want to int anything. We'll just do that. Else instart tokens, just do that. And then so we want to define running running monad, so running a script on a given input. So okay, we'll just call it num. And Might as well be a string, not an integer, because we're sort of feeding digits in. So let's say num index equals 0. And then we have to set the variables, so they said I've got a dictionary here. Variables equals w 0 y 0 z 0. Is that everything? Yeah, Z is used for the output. Okay, let me just have to do a... How do you do Python switch case break again? Okay, so we go for... Let's call it instructions. Instruction, or actually let's call it ins0, ins1, ins2, or I think it makes more sense to that's fine. All right. In instructions, I don't remember how to do this switch case break thing. Python switch case match. Okay, so match ins o case imp. Alright, so if it's imp, we do read an input value and write it to variable A. Okay. So variables, or variable, let's just call it variable. Int1 equals int of num index, and then just push num index forward by 1. Okay. Add. Alright, we need a little inline method here, in a local function here. Get val if k dot is digit, return int k, else return variable k. Okay, so we get the value or by reference. All right, so case add Variable ins1 equals and then this pattern is roughly the same for all of them, so let's just copy this a bunch of times. So this is mul. Yeah, I don't see any way we can go negative anyway. Mul weapons equals that times div that mod that equal, so it's going to be 1 if A and B are equal. Basically that. Okay, that's right. That is how to run the program. You can just try all possibilities. So how do we do this? We just want to. It's gonna be iter_tools. I think for the next part they're probably gonna make it longer, make it a longer string. From iter_tools import. Oh, I always forget which one's which. Cartesian product, isn't it? Product. Gonna be 191919, so or R in product. It's gonna be nine four 14. Does that work? So that's not iterable. It just takes the first character and the next character. Print this. I just want to see what it looks like. That's not right. Okay. How does this work? I forgot how product works. I have to go online. Hang on. All right, iter_tools product. Oh, I see. You don't do that. We don't... If I wanted to do this, I would have to basically do that, and then do like star whatever to pass it in as an argument. Except I don't need to do that because you just use cycles equals 14. Wait, what was it called? Repeat equals 14. There we go. Right, so then the string, the imp will be join R. What were we trying to find again? Best largest model number accepted by monad. Okay. Largest equals 0. If we didn't do anything with this, define run, and then we return true if 0 is in Z. Okay, so return variable Z equals 0. There's no like loops or things like we often have in those int codes, so it's just like a one pass thing. Alright, so if run imp, let's call it num to be consistent. If run num, largest equals max largest int num, print largest, go. Hang on, what happened here? Not enough values. Expected 3 got 2. Did I not put... Oh, that should be imp, not ins. The error -8. I got a negative number? Oh, you do have negative numbers. Okay. Okay. So we can just do a little hack here. The proper way should really to be use regular expressions or something. But we can just say if k, the last character, is digit. If k is a last character. Zero. Huh. 1, 9, 14. Alright, I might not have used the right things here. Submarine model numbers are always 14-digit numbers consisting only of digits 1 through 9, not 1 to 9. Oh, that changes things. That actually makes it easier. And then we just count down from 99999. Which I could have done anyway with that approach, but I was just cutting corners. But we just have to watch out for digits 0 appearing, so... Like, it's a big number. So it might be a long time until we actually find one. You can cut out a lot of work by skipping the zeros when you're counting down, but that means you have to write your own decrement method, which is not too hard. Okay, let's just try for R. How did I end up thinking it was 1 or 9? Yeah, no, it wasn't. It's 1 through 9. Okay. I have a feeling they want us to actually figure out what this is doing. I mean, it's only... It is 100 instructions, so being able to reduce it to like 3 instructions would actually be save time. But anyway, let's just try for K. I don't know why I want to call it K now and not R. K in range. Right, well, we just break. I don't know if this is actually gonna work. Okay, so so if run. Okay, so if run. S equals string of num of k. Well, num equals string of k. If 0 in num continue. If run num print k break. It's gonna take forever, isn't it? We can get a sense of how many we're getting through. Alright. We need to what actually affects the Z? Oh, the very last instruction does affect Z, so we can't just stop early. They're not going down to 0, the number has a constraint you missed. Well, I mean, I know that's not a valid number. It wouldn't matter because I don't expect to get that close anyway. I can put smallest value viable number, which would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Put 0 there, technically. But I don't expect it to get anywhere close anyway. Looks like we're actually going to have to do some thinking about this, what's actually happening here. Well, I mean, it is a linear pass, so it's actually... you can just figure out what this actually ends up being. Interesting. So the Z is only when we... Okay. How many times does this come up? 14 times. So we do 1 for every digit. So it's actually... sum of the y's, each of these. And they're independent, are they? Multiply x by 0. By 1. Yeah, it looks like it refreshes them. We'd have to check each one by one to confirm that. But then that simplifies things. So in order for z to be 0, every single one of these should return 0. That tells us what each of those digits would be. Okay, stop running this. Do we do this by hand? Okay. No. We can just well, I should have a quick look and confirm that that is actually true. X is initialized to 0. Oh, hang on, we're playing with Z. Why are we doing that? Divide Z by 1. Okay. Multiply y by 0. Multiply z by y. Oh, okay, it's not actually that simple. So we always end up multiplying it by y and then adding y. In order for all these to be 0, well, yeah, but y could be negative. So it's not actually independent. We can't just make all of these 0. It could be that y becomes a really big negative number. Well, looks like I'm gonna have to actually figure out what each of these are doing. Can we confirm at least that x and y are initialized every time? Yes, looks like it. Let me separate these properly. So x is 0, y is 0. 0, y is 0. Why does it do div z by 1? Strange thing. Alright. 0, y is 0, okay. 0, y is 0. Okay, so x and y safely start at 0 every time. Yeah. Okay. That's useful. And then Z. Yeah. Div Z by 1 is just a dummy operation, isn't it? It's not actually doing anything. Okay. So the actual only operations we do for Z is add the Y's. It's really a case of building a Y using... What does W get used for? Alright. Okay. So if we could figure out the 14 Y values we need, then that would then you would just reduce to solving those independently. But I guess we need to find out if Y is always positive. Because if it is, that basically turns it into independent problems. Let's have a look at this. Right, as long as we're not using negative numbers, the moment we use a negative number, then the numbers can be negative. So far those are all positive. Okay, add x minus 8. Interesting, so that turns it positive again. So that means we're back in the positives. Okay. Again, it's safe because this becomes positive again. Is this the key? Is this basically the number we want W to be? Not quite, but I think that we're basically there. We're almost there. We just need to... Okay. So we've confirmed that these are now fully independent problems. All the Y's have to be 0. So... this should really just be 14 separate programs, right? And when we see the next imp, we create a new program. Let's just try and code it that way. And then we can just try 9 different numbers to find what makes it 0, and then once we know all there maybe multiple values that do that, then we have a Cartesian set. All right, let's see what it looks like. All right, so let's call it programs. All right, so we go program equals that. If we've got an imp, then we just do this. Oh, why do I? Okay, we don't need that. Programs dot and empty list. So that's the new program. We do programs last one, append that. Else programs the last one, append that. It's all going to break now. Let's just look at programs. So we should have 14 programs now. Okay. Now, for I in range 14, we need to make Z 0. With so it still this program still returns, yeah, still returns that variable as is. Okay, so we want for I program, hang on, let's call these solutions. Or program in programs. Solution is an empty set to begin with. For I in range, it's not allowed to be 0, so it'd have to go 1 to 9. If this has to come afterwards. Run so this time this says we have a program and a W. So we'll just put W in there. X is 0, Y is 0, Z is 0. No, we don't have that anymore. Put that. In fact, we don't need the imp W. Take that one out. Okay, take that out. And then match. So we take that out. This. Yeah, we'll pass that in as an int. And then the rest is all fine. Then if run I just had a look at my code and I remember why this was day 24. A problem that looks simple but requires proper analysis. Yeah. Well, let's see what part 2 is gonna throw at us. I feel like this is correct. It looks independent. If run I solution dot append I it run program I. So then what we should have is just a bunch of allowable values for each of the digits. And you would just take the biggest of all of them, wouldn't you? And we got 0 solutions. Okay. Why did I put... Oh yeah, because I didn't append the solution. Wait, is this... Hang on. Maybe my assumption here was wrong. Wait. We're adding the Z. Oh, damn it. I didn't even notice that instruction. That changes everything. That means we're carrying stuff forward. So we have to work backwards from the last program then. We have to say... We need to know what... So the Z from the last one gets put into the X. Okay. Is that always the case? Yeah, it looks like it. So X is set to the last Z. So we need to know what pairs of values, the W and the X, Z actually. Would solve this. And work backwards from there. The last one we want to make Z 0. Let's just try running that last program, see what actually happens. Say for W in 1 to 9, Z in Z could be anything. It'd have to be positive, but what's the worst it could be? I don't know, let's try 100 for now. That should be a range. If so, okay, so okay, so the program actually needs a Z, and Z set to Z. And we want the Z to end up being 0, at least for the final one. Okay. Let's just see what this final program, if run, would be programs -1. WZ. Let me just print WZ. Let's see what happens. 1728. So, fine. Well, that's nice. Okay, so it's saying that Z has to be W plus 6. I shouldn't manually do these one by one. I should, okay, so how do we do this programmatically? Basically have a table of values. This 100, I just pulled it out of nowhere. What is the could there be multiple? No, because it's a linear expression. Well, it's not linear, but it's an expression. An arithmetic expression. Um, so we could just do this. We can just say okay, so we have a way of figuring out what Z is needed for a given W. Now, this is the rightmost program, so it's actually the least significant bit. So we need to take biggest... Oops. I mean, what this tells us is if we're carrying forward 7, 8, 9, 10, 11, 12, 13, 14, each of those, then there is a W, the last digit, that will force it to be 0. So that gives us an allowance. Is it always going to be a linear range? Because if so, that's good. So then we could just work backwards and say, okay, given so we're saying the last program has to have returned Z equals each of these, and in each of these cases, we know what W will fix it. All right, okay, it's starting to come together now. It's confusing though. Okay, why don't we just try and compile all these programs one by one? So, starting from the end and working backwards, we always have a target set of Zs. In this case, the target set is purely just 0. And that target set grows as we go back through the programs, as in the allowable Zs. How do we do this? Okay, so for program in backwards. So we start off with target equals zero, guess. So we basically do this, we say for each of the W's we could feed into this. I'm getting confused now. What am I actually trying to do here? We're not trying to maximize the W's as we go along because we care about the biggest W right at the back. Okay. So we don't actually. Okay, this is not get rid of that. We will actually return the value here. Run returns that. Okay. If so for W. Let's just make a map here. Needed W or wait, do we care about which? Well, okay, that's not an if statement. Okay, so make this a set. If run programs in target that means, okay, that we can hit our target. Then we want the Z to be the new target, basically. So this Z is the one that came from before, and that value is what we need. But furthermore, we know the W we would need for that given Z. I guess we can put that somewhere as well. W needed for Z equals that. W. Then what? Now we have a new target set. What are we doing with this? Just put it in a list. Maps equals list. Put it at the front. Let's just run that. It'd be 0. And then I just want to see what this looks like now. No. Apps. So it's saying this first map is saying we can either go with 189 or we can go with 0. W we need for each of those is 1 or 8, and each of these will lead to a final 0 if we follow the right path. So if we pick the 8, then we'll pass the 0 on. Wait, no. We have something in front of us. I'm just not clicking for me now. Hang on, if I change this, could there be multiple? I think that's too big. I think it can. Oh, interesting. Okay, fine. Alright. Let's half get it. I think I need to think this. I think this is going to be another case where I don't finish today. I think I need to think this over again. I need to get some pen and paper out. I can't just look at code for this one. But I can half see what is needed to be done. I just can't put it in the right order. I mean, could we run this? Could we do it recursively? Actually, it probably won't be too hard, will it? We just say, actually, yeah, I think if I write this recursively, it actually is much easier. Let me try and do that right now. We want to find the biggest Alright, let's see. Define get solved by hand for my data originally, then went back and solved an input. Yeah, that's tempting. I think recursion will work here. There's only 14 things, so I get biggest W that will eventually lead to 0. That can eventually lead to 0. Okay. And we're given an index because that's what program we're looking at. And we know what the base case is. It's the final program. Given that Z has been passed along this program. That's what we want, right? We want this general function, given an index, i.e. which program we're looking at, and Z, that number Z has been passed in, we want to get the biggest W we can feed in as input that can still allow us to get 0 by some combination of all the remaining programs. So if we can solve this recursively, then that will then give us the correct digit for this one program, and then we push forward. And if we memorize this, am I thinking about this correctly? So let's see. So we just try all W's. For W in range 1 to 9. Result equals programs index to be run, programs index for that given W and the Z that went in. And then we have to make a recursive call to the next one. So we say if we don't find any solution, Okay, so largest equals none. And we try to find one. Leave that blank for now. If largest is none, then we return so the idea is now we call if get biggest W, we now call the next one. I haven't done the base case yet. But this given Z is not none. That means it's possible to find the combination for that one. Then we found biggest one. I mean, shouldn't we just work backwards? Because we don't actually need to do all these steps. We can just say, this is the moment we find one, then we're done. In range, so starting from 9. If then we return W. We found the biggest W that works. And then if we get to this point here, we just return that. Yeah, that's better. Okay. But if index is length of programs -1, that means we're in the final one. We want well, no, we don't do that. We say or W in range blah blah blah, result equals that. If index is if we're in the last one, then return at so there's two cases. Either it's the last one, in which case result has to be 0. If result is 0, return W. Otherwise, we try the next W. Is that all right? And if we're not in that case, then we just do that. And of course we have to memorize so that we don't repeat these. And then let's see if we can get the first W. So we want to get biggest W 0, and then the Z is going to be 0 by default for the first one. How long is it going to run? It should. The problem is Z is a kind of an open-ended number. It can take a lot of values. It might be that we have to crack the actual pattern here. Apparently there's a lot of Z values. Hey, wait. Hang on. Get rid of all this as well. Look. Yeah, that was... I don't know what I was doing there. Alright. Get rid of W. Alright, if we manage to find an answer to one of these, just like, print index, I guess, I don't know. I don't think this is the right approach then. I think we do have to figure out the pattern. It's too many Z values. And the final thing was just like, Z just needed to be like W plus 6 or something. Oh, because it's the modulo operation that really changes things, because that's a many to one. So is div, but... Let's make sure we can actually get small. I don't know, like 12, start from 12. Okay. Go for 7. Further back. Okay. Okay, biggest W. So the answer to that is 9. Back to 4. What? Why is it running so quickly for these? I don't understand what's going on. If I go to 0... Something strange is going on. Alright, so that's the... that doesn't make much sense. It hangs for 0 and everything else is just instant. Also, the numbers don't look right. Like, why is this... Why... Like, we got 12... No. W in range, 9... X is always set to Z. And Z gets set back to... Huh? What does this mean? So it's... X and Z are the quotient remainders of dividing by 26. Oh, okay. Oh, I see why it was quick for these, because we were putting 0 in. So it's really easy to do when you push 0 in. But for the first program, Z is 0. The others we're just kind of setting X to always be 0. What's special about this number 26? Is this like number of characters? The alphabet? Interesting. Okay, so basically, this method may well technically work. It's just too slow. The correct answer we'd get would be if we did W. The first one and 0. So that would give us the correct answer. It's just it won't run. Okay, fine. And we can't just increase this to 1 or something because the Z would no longer be valid. Okay, fine. How far does it manage to get then? Like, so this print index, how deep are we getting into this? It's going to print a lot of indices though. Wait, what? We get all the way to the end. But we often... Okay, fine. So we go all the way to the end. But we're not hitting our target. I see. Alright. So the recursive approach doesn't really work because there's just too many Z values. I think we just have to work out what this program actually does. One second. Alright. It might actually just come out to be so simple if I just look at it for a bit. So, let me just try and write out what is happening here. So we've got X is Z. So when we first input W, Z is 0. Well, we'll just keep Z as a variable, so Z. So X is set to Z. Let me just... copy these instructions somewhere. Okay. Right. Zoom out a bit. Alright, so... Alright, we'll just do it above. So we say... X equals Z. Alright. So get rid of that. Z percent 26. Z is now Z divided by 1. Just keep that in there for now. This one, we add 14. Equal X to W, so if W matches that, so basically it would have to be Z would have to be above something. And to begin with, Z is 0. So X would be 14. So W would have to be... Wait, what? Well, I mean, it depends what we actually do with this. Okay, so this X is now basically W equals that. I should use colon here, the equals is a bit confusing. So X is now that formula, basically. And then we say if this is equal to 0, so not equal, basically. I see. Okay, that makes more sense now. And then Y is 0. It's 25. Y is 25. Okay, so we don't deal with X anymore. So now Y is basically 25 times that. Okay. Okay, we don't care about X anymore, I suppose. Oh, we do. And 1. What? This is not making anything clear to me. What is going on here? You got two cases basically. W. Yeah, we should just split it into the two cases where W is this and W isn't. Say case 1. W is that. Which it can't be to begin with, but let's just see what the formula is unfolding to. So then in this case, we are looking at zero there. And that becomes a 0. Y becomes 1. I need to make sure I'm keeping track of which instructions we got to. So that is case 1. Case 2. X is 1. Y is that's a 1. That's 25. Y is 25 plus 1, 26. Z is Z divided by 1. So those are the two cases. Then just look at the next step. Multiply Z by Y. Okay, so it's going to be... Just keep the 1 in here just to help me see what's happening here. 56 times that. y is set to 0. And then add w to y. Okay. And then add 12. Multiply y by x. Okay. So that is 0 in that case, and that in that case. And add y to z. Interesting. And like when z is 0, that becomes 1 plus w plus 12, so w plus 13. And then that becomes w plus 12. W plus 13, w plus 12. Wait, no. When z is 0, it's w plus 12 either way. Okay. So the first program adds 12. Oh, bad. I don't even know if I did that right, but okay, that's sort of what it looks like. Okay. Now let's try program 2 because this time z will be a variable. It's gonna be really similar, isn't it? Okay, so we have x, y, we've got z, which is passed in. Alright, so x is set to 0, x becomes z. And then percent 26, y by 1. Alright, so it's basically always the same pattern, but there's just some numbers that change, aren't there? I need a spreadsheet. I need to put these side by side. Or in the spreadsheet. I just want to see which numbers stay the same and which numbers change. It looks like I think this is all going to come down to giving us an alphabetic message because it's 26 characters. But these are the... That doesn't matter right now. I want to stop. Well, I'm still on part 1, so we're not close to finishing this. Look at this again. So, okay, so this was divide z by 1. This was divide z by 1. This is divide z by 1. Now it's divide z by 26. And then divide z by 1. Divide z by 1. Divide z by 1. Divide z by 26. It's always 1 or 26. Whenever it's 26, we seem to be subtracting. Oh, everyone loves int code. Yeah, I think the next step is I need to open up a spreadsheet and look at these. I just want to see them side by side. That'll help me see what's going on. Yeah, there's a very clear, and I want to confirm that every instruction is the same in each of them. Can we do this within the IDE? I suppose we can. Whatever, I'll figure it out next time. I don't think there is really a... I think it's one of these problems that doesn't have a proper code approach. Like the final one, you want to make that 0. We already established that you have to add 6 to W or something like that. Yeah, when it's a... Alright, worry about it next time. Um... Okay. That's it. I guess we'll carry on tomorrow. Bye-bye.